All right, so in this video, we're going to talk about how to find the pH of a mixture of a weak acid and a weak base. And that's otherwise known as a buffer, when you mix together a weak acid and its conjugate base. And we're going to introduce in this video the Henderson-Hasselbalch equation and talk about how we can use that equation to solve for pH. Okay, and some things, just kind of overview of buffers, since this is where we apply this equation. Buffers are solutions that resist changing pH, which means that if you add base or you add acid to your buffer solution, the pH will not change by very much. And the way that you make a buffer is by mixing together a weak acid and its conjugate base, or a weak base and its conjugate acid. And how buffers work, the reason why buffers are effective is because if you have a mixture of a weak acid and its conjugate base, if you were to add some strong base, some hydroxide ions to the buffer, your weak acid component of the buffer is going to act to neutralize that strong base that you form. And it's going to turn that into A- and H2O. So it's going to produce some of the conjugate base. If you add, which remember is already present in solution, if you add acid to your buffer, then some of that conjugate base is going to turn back into the weak acid. And it turns out mathematically, if the concentration of your weak acid and your conjugate base are within tenfold of each other, the pH is going to remain within plus or minus 1. So it's pretty resistant to changing of the pH. And let's look at how this works out mathematically here. So we're going to be looking at this equation right here, which is the Henderson-Hasselbalch equation. But this equation, it looks new, but it's actually just a different form of this equation right here. So let's look at how this equation is derived. So we know that for an acid, your Ka, the kind of general format of it is this. Ka is H plus times A minus over HA. It is the K for this reaction, where your acid dissociates to form ions when you put it in water. So to get to this equation down here, what we would do is we would take the negative log of both sides. Let's say we took the negative log of both sides. The negative log of Ka is equal to the negative log of the H plus times the A minus over the HA. All right. And because of how log rules work, is we could rearrange this and say that the negative log of this is the same as the negative log of H plus the negative log of A minus over HA. And then this is the negative log of Ka. And if you're wondering why we did that, well, now you might recognize, oh, hey, negative log of H plus, that is something otherwise known as the pH. So let's just call this the pH. And we're going to leave this as is. And then the negative log of the Ka, we actually have a special name for that as well. If we take the negative log of the Ka, we call it the pKa. So you might notice a trend here. The negative log of H is called the pH. The negative log of the OH is called the POH. The negative log of the Ka is called the pKa. We also, if you take the negative log of the Kb for a base, we would call that the pKb. So when you stick a P in front of something, that means you take the negative log of it. So this thing, we're going to call it the pKa for short there. And then if I were to rearrange this, I want to make it so pH is by itself. So I'm going to add the log of A minus over HA to both sides, right? In order to get this to, now they cancel out over here. So we end up with this equation that the pH is equal to I'm going to write it where the pH is on the left. So the pH is equal to the pKa plus the log of the A minus concentration over the HA concentration. There we go. We just derived this right here, which is known as the Henderson-Hasselbalch equation. And it is a way, it's an equation you can use to solve for pH if you know the Ka and you know amounts of A minus and HA present in the solution. This is not an effective equation to find the pH of just a pure acid. So if someone says, like, what's the pH of 0.1 molar hydrofluoric acid, you could not use this equation to solve because you only have HF in it. Okay, we don't have the conjugate base. But if you're trying to find out what is the pH of a solution that's 0.1 molar HF and 0.1 molar F minus, if you have a combination of both the weak acid and its conjugate base, then yes, you could use this equation to solve for the pH. So this equation is only useful when we have a mixture of a weak acid and its conjugate base, otherwise known as buffers. So we should be using this to find the pH of buffers, not for just a pure weak acid or weak base. Okay, and here's another visual over there of this equation. That's our Henderson-Hasselbalch equation. So let's do some practice calculations involving both the, Ka, pKa, and the idea of the Henderson-Hasselbalch equation here. So first, let's take a look at pKa values. So let's just kind of get familiar with this concept of pKa. So to get the pKa, you take the negative log of the Ka. So you want to make sure you actually practice doing this and plugging it in your calculator. But if you take the negative log of, for example, 6.2 times 10 to the negative 10, you get 9.21. So we'd say that hydrocyanic acid has a pKa of 9.2. Acetic acid, if you take the negative log of it, it has a pKa of 4.74. And then if you want to hit pause and do that for the other acids, please do so. And then you can check your work here. I'm going to put in the pKa values here. Make sure you actually practice doing this in your calculator so that you are familiar with the correct buttons to use. All right. So let's take a look and find the pH of a buffer where you have equal amounts of HA and A minus. So let's say I've got a buffer made with 1 molar HClO and 1 molar Cl minus ions. We know the Ka of HClO is given to us in this table. So the Ka is 2.9 times 10 negative 8. We also already found the, oops, that looks a little weird. We also already calculated what the pKa is. It looks like it is 7.54. So since I have a mixture of a weak acid and its conjugate base, this is a situation where I can use this equation right here, the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation tells me that the pH is equal to the pKa plus the log of the A minus over the HA concentration. So my pH is equal to 7.54. So take the negative log of the Ka here, plus the log of, in this case, it's 1 molar acid, 1 molar conjugate acid and 1 molar conjugate base. And if you were to go through and you plug this in your calculator, you will find that the log of 1 is 0. So that means that the pH is just 7.54. So what we just noticed here is that when the amounts of your weak acid and your conjugate base are equal to each other, the pH is equal to the pKa. So in this case, the pH is equal to 7.54. Okay. So thinking about buffers, we will notice that buffers will typically have a pH that is close to their pKa. Because when you have a buffer, you're going to have relatively equal amounts of the weak acid and conjugate base pair. So that means that this value, the log of that ratio, is going to be close to 0, if not exactly 0. So we're going to end up having a pH being close to what the pKa is. So that's a way that we can choose. So like, let's say we have this scenario. You want to make a buffer with a pH of around 9. You're trying to figure out which two things should I mix together to make a buffer with a pH of around 9. Well, I would want to find a buffer where the weak acid has a pKa close to 9. So if I'm looking at these options, you'll notice that these right here are the options from this table we did up here at the top. So I want to find which of these acids has a pKa close to 9. So like HClO has a pKa of about 7.5. HCN has a pKa of 9.2. Ooh, that looks promising. So if I mix these together, I should get a buffer with a pH of around 9. Let's double check my other options. This one has a pKa of around 4.7, so that would give me an acidic buffer. HCN and HCl, well, that's not even a conjugate pair, so that's not going to work. And these ones are also not even a conjugate pair, so those aren't even buffers. So my top three are all buffers. They're all weak acid and its conjugate base. But this second choice is going to be the best one because the weak acid HCN has a pKa close to 9, and I want to have a buffer with a pH of 9. All right, let's look at another application of the Henderson-Hasselbalch equation. So we want to make a buffer using acetic acid and sodium acetate. We find the pH of the solution and determine that it is 4.9. And then it's acetic acid. So let's look back at our table and say, what else do we know about acetic acid? Well, we know acetic acid has a pKa of 4.7. pKa is 4.7. So the question is, we want to compare the concentration of the weak acid and its conjugate base. So which one's greater than? So one way we can solve this is we can use the Henderson-Hasselbalch equation here. So here's our Henderson-Hasselbalch equation. So we know that the pH is 4.9. We know that the pKa is 4.74. So I see that my pH is greater than my pKa. So my solution is more basic than it would be if I had like equal amounts of acid and base. So I'm going to predict that I have more of my conjugate base than my acid, since my pH is a little bit higher than what my pKa is. I can actually double check this mathematically though. So let's rearrange this. So 4.9 minus 4.74 is going to go on the left, and then on the right is going to be the log of the A minus over the HA. And so I end up, let me get out my calculator here. So I end up with the systems of being 0.16 is being the log of your A minus over your HA. So to find this ratio, let's take the inverse. We're going to raise everything by 10 to the power. So what we're saying is 10 to the power of 0.16 will give us the A minus over HA ratio. So if I plug that in my calculator, 10 to the 0.16 is 1.4. So what that means, I can rearrange this even further if I want to and say A minus is 1.4 times my HA concentration. So that means that my A minus is going to be more concentrated than my HA. So if I were to plug in a number, like if this were 1 molar, my A minus would be 1.4 molar. So that means that in this buffer, I have more of the weak base than the conjugate acid. And that's what I predicted up here. So we'll notice this, that when the pH is higher than the pKa, that means you have more of the weak base. If the pH is lower than the pKa, you'd have more of the weak acid. If the pH is exactly equal to the pKa, that tells us that the amount of the weak acid and the conjugate base are exactly equal. All right, and here's another application. Let's look one more example here. Your pH equals your pKa plus your log of your A minus over your HA. Let's look at another application of this equation. So we have a solution. It's got a weak acid and its conjugate base. That's the first step, is identifying that we actually have a conjugate base here. So here is my weak acid. And then this right here looks like the conjugate base here. That's the CHO2 ion. Remember, you can recognize a weak acid and its conjugate base because they differ by just one hydrogen. That's how their formulas look exactly the same, except one has one more hydrogen than the other. So we got this conjugate acid-base pair. So if I go and plug this in to find the pH, remember I already found, let's see, did I already find the pKa of this one? I think I did. Here it is. So here is my acid, methanoic acid. It's got a pKa of 3.74. So the pKa is 3.74, and then I'm going to take the log of the A minus over the HA. So my A minus is 0.15, my acid is 0.2. So if I'm going to plug that in my calculator, and again, make sure you're actually practicing plugging this in your calculator so you know how to use these buttons there. I end up with a pH of 3.62. So notice how in this case, my pH is a little bit less than, my pH is less than my pKa, which makes sense because in this buffer, I have more of the acid component than I do the base. So again, if these two things would be equal, the pH would equal my pKa. Let's write this down. Okay, so if my HA and A minus are equal, then my pH is going to be equal to my pKa. If I have more acid than the base in my buffer, I'll find my pH is a little more acidic than what my pKa is. And if I have more base than acid, then it's going to be the reverse. I'll find that my pH is a little more basic than what my pKa is. All right, thanks for watching.